Okay, hi, and thank you for all the organizers for inviting me here to Vienna. It's always a nice excuse to come and visit Europe, come see everybody here. So today I'll be talking about my PhD work in the group of Holger Mueller at UC Berkeley, where we worked on a cavity-trapped atom interferometer for probing all sorts of potentials. And I'll kind of, yeah, that will be the main focus of my talk. And just as I get started, maybe I can just show some kind of nostalgic slides maybe for Philip here. This was us back in maybe 2017 or 2018 working on the setup in Berkeley, where, yeah, this is our atom interferometry experiment. And today, the main thing I'll be telling you about is how we reach the 20-second coherence time in a largely trapped geometry for light pulse atom interferometers like we've heard so much about today already. And just to say now, since finishing up my PhD work at Berkeley, I've actually, now I'm working with the LIGO detectors in person, both in Washington State and in Livingston in Louisiana State in the US. And that's another reason why this conference is actually very exciting. It's cool to see the convergence of, quantum metrology, astrophysics, like we've heard so much about today, because a lot of the work that we're now really doing in the labs is really making big gains for astrophysics. So this is a nice conference to bring all these sides together. And so today I won't be telling you so much about laser interferometry, where we, again, diffract, use actual materials to diffract light waves, guide light waves to perform interferometric phase measurements. Instead, I'll tell you about atom interferometry, where we use pulses of near-resonant laser light to steer matter waves around, and we read out the phase from interfering matter waves. It's a little bit of a reversal of the roles compared to traditional interferometry with light. So this is just some of the people involved at Berkeley. Philip, of course, Paul Hamilton, who's now at UCLA. And I want to especially point out Matt Jaffe and Chris Panda here, who Chris Panda is now the postdoc leading this experiment. And Matt and I worked together for many years on the results I'll show you today. So we've heard so much already about atom interferometry, but if I can just give a very quick recap here. One way I think about atom interferometry is you essentially have these little atoms, they're falling through space, and as they interact with the laser beam, they get a phase shift imprinted from the d.e interaction, which has this I to the kx term. As atoms move, obviously, their position changes with time. We read that out through comparing the total interferometer phase at the end of the pulse sequence. And one thing to note here, of course, is that there's a factor of K effective that enters into this phase shift. And that's what makes atom interferometry such a great tool for actually precision measurements, because you get something like 2 pi radians per micrometer of displacement. So this is a huge lever arm for making very precise inertial measurements, inertial in the sense of you can measure how the atoms are moving from the precision you have in measuring their positions that guide their trajectories. And of course, this has now kind of become a well-known tool to measure, for example, Earth's gravitational acceleration in the lab. And so moving forward, our kind of take on this is not simply using the Earth as a source mass for our gravitational measurements. That's to say, we're not just measuring 9.8 meters per second squared as sourced by the Earth. We can actually toggle the location of a mass inside of our vacuum chamber and do experiments where we use the atom interferometer as an accelerometer to measure effects that are sourced by this mass inside of our chamber here. And so you can see how our experiment runs on the right side. There's a cloud of laser-cooled atoms cooled roughly an inch or so below the source mass. I think Philip took these 2 pictures, in fact, on the right. But this cloud of atoms in traditional light pulse interferometry, for example, in a Mach-Zehnder sequence, there are 3 laser pulses during the interrogation time. So what we do is we cool a gas of laser-cooled atoms underneath our source mass. We throw them up towards the source mass, and we measure the position of the atoms using the laser beam at 3 points along this trajectory. And from that parabolic trajectory, we infer the acceleration that guided that trajectory. So that's really how atom interferometry functions as sort of this accelerometer here. And to start, let me just explain a little bit how we did this precision measurement of an attractive blackbody force using this setup. So we've already heard so much about this. I'll just go very quickly through. Blackbody radiation, most of the power spectral density from blackbody, an object emitting blackbody thermal radiation, is very far into the infrared. There's very little overlap between blackbody radiation and the visible spectrum, and most atomic transitions are, let's say, a micron or less. So the amount of incoherent photon scattering that you get from blackbody radiation on atoms is actually very small, just spectrally. However, blackbody radiation is far detuned from atomic resonance, or might remind you of a far red detuned dipole trap. And exactly, there's an intensity gradient in the intensity, which of course there is because you're radiating thermal radiation into a larger and larger sphere. There's an intensity gradient as you move away from the hot object. And together, the intensity gradient plus the far red detuning makes it seem like a simple kind of red detuned dipole trap, which is, say, an attractive dipole trap that traps atoms at the hot spots of the intensity, as opposed to a blue one that trapped at intensity minima. And so this was the proposal from Matthias, Monica, and Helmut, as Helmut said, almost 10 years, basically 10 years ago now. And in fact, Matthias did these simulations for our source mass in our vacuum chamber to say, if you look at the acceleration profile from this attractive blackbody optical dipole force, how does this look as a function of trajectories on our experiment? And what you can see is right as you enter the bottom surface of the cylinder, that's when the blackbody acceleration is the strongest. And something that is markedly different, as I'll get to, between free fall atom interferometry like we're doing here and trapped atom interferometry, is that, of course, if we can only use the atomic free fall trajectories to infer the acceleration, you're never going to be able to do something like, for example, move the atoms into the most sensitive spot of the potential gradient and directly sense such a localized source. The best we can do is optimize the ballistic trajectory of our atoms that fly nearby the object, and we can try to kind of park and launch in the most sensitive regime. So that's one very big difference, as we just heard nicely about. So how we do this precision measurement in practice, again, the source mass in vacuum is movable. We move the source mass near the atoms and then far away from the atoms. And these are the two positions we kind of toggle or chop this effect in between. And as a differential accelerometer, we can take a lot of data, seeing what is the acceleration, for example, as opposed to Earth's gravitational pull. Philip had a actually like genius and crazy idea to shine in like a 7 to 13 watt infrared laser from out of vacuum to heat up the source mass from the outside. This was actually nice because this could heat up our little source mass about 100, increase the temperature by 150 Kelvin in something like 10 minutes just with laser heating. And in a single cool down, what you see here is about a 3-hour cool down and what the measured acceleration looks like when the sphere is near, for example, versus far from the atoms. And we can do this then many times to average over many, many cooling cycles. Doing the same thing, you heat up the cylinder, you do atom interferometry in positions of the source mass being near and far, and you look at the relative differential acceleration near the object as the object cools. And we do this many times, and we see a very nice spectrum of an acceleration that is attractive, meaning inward pulling towards the heated object with a power that scales with the predicted quartic scaling of blackbody radiation compared to the outside ambient temperature. And I just want to point out one more thing about this is that, of course, once you come back to room temperature, even once there's no difference between the outside, between the source and the external temperature, of course, this curve will not go to 0 because at all temperatures, the source mass actually does have, of course, a gravitational pull, and that's what we see here. This curve doesn't go to 0. It actually goes to about 70 nanometers per second squared of acceleration, and that's the gravitational pull of this 1-inch, say 2.5 centimeter object itself. And this was very nice work led by Matt and Philip that actually by measuring the gravitational pull of this object as we had done previously, the absence of anomalous forces in excess of the gravitational attraction actually allows us to constrain a range of dark energy theories. So this is very nice. Okay, and then we can move on a little bit, and we've heard from Dennis today an amazing talk about the incredible work that goes into constructing long baseline atom interferometers that are 10 meters or so. There are all sorts of efforts to bring atom interferometers into space, into microgravity environments, all in an effort to maximize the inertial sensitivity of atom interferometers, because you see the interrogation time t squared, the sensitivity, the phase sensitivity of atom interferometers to inertial effects grows with the interrogation time squared. But that, of course, quickly leads you to building these sort of long baseline atom interferometers. So it was an idea over 10 years ago and demonstrated how you could actually use light pulse atom interferometry and do a pulse sequence where you could actually try to trap the interferometer mid-flight. And this was, I think Philip had a question about this in the last talk. So this pulse sequence is doing essentially 2 optical Raman, 2 photon beam splitters. Once atoms reach the apex of the trajectory, you trap them in an optical trap, for example, an optical lattice. And as they fall out of that, you add 2 more laser pulses to recombine them. And these first experiments, given their relatively near detuning of their lattice hold, got out to something like 100 milliseconds or so. And later, this experiment was done again in Italy, in Tino's group, using a very far detuned optical lattice hold, reaching about 1 second of hold time out here. And they actually realized that once you could overcome the limits of your detuning, what they then found was the limiting factor was the quality of the optical wavefronts of the trapping potential. And so that motivated sort of us to give it a try, because of course our experiment is an atom interferometer. And what it means to be a cavity atom interferometer is to say that the laser beams driving the atomic beam splitters are formed by the cavity mode. That's what it means to say a cavity atom interferometer here. So we have about a 40 centimeter cavity, not terribly high finesse, about 130 finesse. So within our chamber, the atom interferometer is kind of the very central part. And the very nice thing about it is essentially that the fundamental mode of the optical cavity is nicely spatially mode filters. So there aren't random speckle patterns so much. All of those things are very well suppressed. And as well, you can measure the beam profile very nicely based on the response of the cavity. And you get a nice resonant power enhancement, so you can operate at larger detunings without having and get some nice power enhancement from this. And in contrast to a lot of other experiments, actually being an optical cavity means that our trapping potential or addressing potential is much smaller than the atom cloud size itself. So in 2019, we managed to demonstrate this scheme for, so in 2019, we managed to use this scheme that's been used several times already to reach 20 seconds of coherence in our trap potential. And now, recently, since we've been able to demonstrate out to a minute of coherence time of atoms being trapped mid-flight in the interferometer sequence. So maybe I can go a little bit through some of the details now about this. So again, we're using the same scheme with 2 atomic beam splitters at the front and 2 atomic beam splitters at the back there. The total interferometer phase has 2 dominant contributions. The phase that the atoms accrue from interacting with these atomic beam splitters, that we could call, for example, the laser phase. That's what acts as the laser ruler to measure the atomic positions. But in this geometry, the atoms also spend a good amount of time kind of resting and being trapped, I guess, in this spatially separated superposition state when they're trapped at nodes of this lattice. And that allows the gravitational potential energy difference between the upper and lower arms to manifest into a phase shift in the interferometer. And in fact, as you go to very long hold times, that actually forms the dominant phase contribution to your interferometer. And so what we do in our atom interferometer in particular, we vary actually the hold time to vary the amount of free evolution phase in the interferometer. And this is how we've been actually reading out interferometric signals in this geometry. So for example, you can see if we're holding a wave packet separation of 9 sites, we see a fringe frequency of phase accumulation rate commensurate with that exact height difference. And so now let me maybe go through one of my favorite parts of this work. So the case where you are trapping a matter wave, which is really a delocalized matter wave function in a lattice, there's the question of how do I load the lattice to trap it? You can load it in integer level, which is to say split the arms and then stop them when they're exactly an integer number of lattice sites separated, and then re-interfere from 9 lattice sites. That's a very clean way to do this. But in fact, you can also load the maximally kind of opposite situation, which is loading a wave packet separation of, for example, 9.5 lattice sites into this lattice. And then it's kind of interesting to see what happens. We load a wave packet separation of 9.5 lattice sites, but in fact, once they're in the lattice, the matter waves completely delocalize, and you can interfere all combination of the kind of multi-port parasitic interferometer that emerges from this situation. So we can then interfere, just choosing the pulse separation time of the last 2 pulses. We can re-interfere arms that were separated by 9 lattice sites. We can re-interfere arms separated by 10 lattice sites. Actually, we can even re-interfere the upper pair of arms. And then really what we're looking at is a phase shift accumulated by the gravitational potential energy difference of 1 lattice site. In our 866 nanometer optical lattice, that's a period of about 433 nanometers. So that's very nice. And the really interesting case is what happens here when you recombine arms. That is to say, you're interfering this bottom arm with a node that's in between the top 2 arms. You see actually beating fringes, which point to 2 distinct fringe frequencies as 2 distinct rates of accumulation, phase accumulation in this lattice. So you see these, in the Fourier spectrum, you see 2 sharply peaked frequencies spaced apart exactly by the block frequency in the lattice. And this is nice. It shows phase robustness to the initial beam splitter conditions because the trajectories are quantized and pinned down by the lattice spacing. So that's kind of a nice technical perk. Let's go to the really nice technical benefit of this geometry, which is that even at 60 second coherence times, we don't see so much impact from the phase noise that results from vibrations. So typically what happens when you have vibrations, your atom interferometer, the atoms fall along the gravitational axis, but of course the laser beam that measures the atomic trajectory is tethered to the lab as the atoms fall down the gravitational axis. And this varying projection, you typically aliases in a lot of, mismeasurements kind of the atomic position that really in practice translates to phase noise caused by vibrations. So again, the lasers sample the atomic positions kind of suddenly and only a very few times during this entire free fall trajectory. But actually what happens while the atoms are trapped in the lattice is that this is a really continuous phase accumulation. And so what you can imagine is this is in some way avoiding the excess aliasing of vibration noise into the interferometer phase. And actually we can test this theory in a very clean way. Consider the case where you have a single period of oscillation during this continuous hold time. If it's really continuously accumulating the phase, you'll of course accumulate, plus some phi vibration phase that you accumulate minus phi that vibration phase in this cycle. So for vibrations with a period that matches the hold time, we should see actually no net phase shift. For example, the exact opposite case is if you were to have, 1.5 cycles, that imparts a maximal vibration phase into this geometry. And we can drive these vibrations by kind of driving the entire vacuum chamber and sweeping through to measure really the acceleration transfer function. That is, how does a real acceleration get transduced into a phase shift in the interferometer? So we do this with a 5-second hold time, driving a voice coil, to which we used to do vibration isolation, but now actually no longer need for vibration isolation. And we see with a 5-second hold time at 0.2 hertz integer frequencies, we see a nice cancellation of this vibration noise exactly because they kind of match out of and are averaged through by the hold time there. So with that, I can conclude. So what I've described to you today is kind of 2 modes of operation that we've done for atom interferometry. There's both free fall atom interferometry, in which we measured, again, the ballistic trajectory of atoms to infer the acceleration that kind of relates to that trajectory. And that really is using atoms in some way as a classical particle to measure their motion. But with this kind of trapped atom interferometry, which is really enabled by the spatial mode filtering of our optical cavity, we're not really anymore just measuring the acceleration sort of a classical particle in some way. We're really now measuring the accumulated phase shift as it relates to the potential energy of two arms during the whole time. So in some ways, it's really going from measuring accelerations to measuring potential differences, which is sort of only enabled by kind of the way a quantum phase evolution works. So there are nice perks, of course. Long coherence times mean that maybe you could build compact, sensitive setups one day. Suppression of vibration noise is also nice because, you know, whenever you're making inertial measurements, it's hard to tell what's the inertial measurement of interest versus what's just like somebody walked by outside. And again, I think the biggest thing may be that it's interesting that we can now hold atoms to measure potentials versus dropping atoms to measure accelerations. That's kind of a nice conceptual difference here. And we can get large, essentially megaradian phase shifts from height differences of only micrometers in the trap. So that's very nice. And I will just, let's see, I will end here and then take your questions. Thank you.